In this lecture, I will explain about numbering systems. So, to understand addressing used in networking, such as IP addresses and MAC addresses, we have to understand numbering systems such as binary and hexadecimal. They are called also number or numeral systems. Currently used numbering systems are positional systems, in contrast to additive systems used earlier. In the positional systems, the value of a symbol or a digit depends on its position, as we will see in the next slides. The first and most common used numbering system in daily life is the decimal numbering system, which has a base of 10. I started explaining this obvious one to ease understanding the idea of the other ones. Because the base is 10, then we have 10 possible digits or symbols, starting from 0 to the number just before 10, which is 9. Now each number will get its value from its position starting from right, where the first position has a value of 10 to the power of 0, which equals 1. The second has value of 10 to the power of 1, which equals to 10. The third has a value of 10 to the power of 2, which equals 100, and so on. So for example, the number 572 is 2 multiplied by 1, so 2, plus 7 multiplied by 10, so 70, plus 5 multiplied by 100, so 500. Another example is 3604, which equals to 4 plus 0 plus 600 plus 3000. Then we have the binary numbering system, which is used in computers and communications because it is simpler and more effective to deal with signals and voltage as either on or off, or in numbers either 0 or 1. So this system has a base of 2. And because the base is 2, then we have two possible digits or symbols, which is either 0 or 1. In this system, each digit is called a bit, and every 8 bits are called a byte or octet. In decimal, we have powers of 10, but here in binary, since the base is 2, then we have powers of 2, so 1, 2, 4, 8, and so on. For example, let us take this byte 01300101. We can simply add the values corresponding to the ones, since any number multiplied by 0 will be 0. So 1 plus 4 plus 64, which equals 69. Another example is the byte 11010110. So 2 plus 4 plus 16 plus 64 plus 128, which equals 214. And here we have ones more than zeros, so we can just subtract the values corresponding to zeros from 255, which is the value of a byte of all ones. So here we have 1 plus 8 plus 32, which equals 41. If we subtract that from 255, then we get the same result of 214. So we can use this way when we have a bunch of ones and few zeros in order to do less work. And as a side note, we see that numbers end with 0 are even and those end with 1 are odd. So we have seen how to convert binary to decimal, and we have to know how to do the opposite. So how to convert decimal to binary. So the first way is the repeated division by 2 method, where we divide the number by 2 until we reach a result of 0, and we record the remainder of each division step. So let us take the following examples using the same numbers we have seen in the previous slide. So first we had 69. If we divided that by 2, then we get 34, and the remainder is 1. If we divided 34 by 2, then we get 17 and the remainder is 0. If we divided 17 by 2, then we get 8 and the remainder is 1. If we divided 8 by 2, then we get 4 and the remainder is 0. If we divided 4 by 2, then we get 2 and the remainder is 0. If we divided 2 by 2, then we get 1 and the remainder is 0. And finally, if we divided 1 by 2, then we get 0 and the remainder is 1. So here we will stop the division and we will take the remainders starting from the last one and putting them from left to right. And because we have only 7 bits, we have to add one more 0 to the left so that we have a byte or 8 bits. So the result is 0, 1, 3 zeros, 1, 0, 1. Now let us try with the second number, which was 214. If we divided that by 2, then we get 107 and the remainder is 0. If we divided 107 by 2, then we get 53 and the remainder is 1. If we divided 53 by 2, then we get 26 and the remainder is 1. If we divided 26 by 2, then we get 13 and the remainder is 0. If we divided 13 by 2, then we get 6 and the remainder is 1. If we divided 6 by 2, then we get 3 and the remainder is 0. If we divided 3 by 2, then we get 1 and the remainder is 1. And finally, if we divided 1 by 2, then we get 0 and the remainder is 1. If we talk the remainders, then we get a result of 1, 1, 0, 1, 0, 1, 1, 0. Another method for decimal to binary conversion is the sum of weights method, where we find the set of binary weights whose sum is equal to the decimal number. So we add ones only when the sum is still less than that decimal number. So for example, for 69, we know that is less than 128. So this bit must be 0. 69 is bigger than 64, so we need this bit to be 1. If we add 32 to 64, then these will be 96, which is bigger than 69. So this bit must be 0. Then if we add 16 to 64, then this will be 80, which is again bigger than 69. So this bit must be also 0. The same is true when adding 8, since the result will be 72. So this bit must be 0. But we need this bit to make the sum as 68. It must be 1. And the next bit will make the sum as 70. So it must be 0. And finally, we need the last bit to be 1 to make the sum as 69. Let us try now with 214. So we need the 128 and then the 64. And now we have reached 192. Adding 32 will make the result as 224. So this bit should be 0. And we need the 16 to get 208. And then we need 6 to reach 214. And this 6 is just 4 plus 2. Another numbering system is the hexadecimal numbering system, which has a base of 16. Because the base is 16, then we have 16 possible digits or symbols, starting from 0 to the number just before 16, which is 15. But since we need a way to represent numbers after 9 using just one symbol, then letters are used. So 10 is represented as letter A, 11 is represented as letter B, and so on till 15, which is represented as letter F. And again, because the base is 16, Then the first position has a value of 16 to the power of 0, which equals 1. The second has a value of 16 to the power of 1, which equals 16. The third has a value of 16 to the power of 2, which equals 256, and so on. So, if we take the hexadecimal number 5C as an example, that would be 12, which is the value of the letter C, multiplied by 1, plus 5 multiplied by 16, and the result will be 92. We can also convert binary to hexadecimal by converting each 4 binary bits into one hexadecimal digit, and that is because 16, which is the base of the hexadecimal, is equal to 2 to the power of 4. So here in this example, these 4 bits are equal to 15, so F. The next 4 bits are 7, and the last 4 bits are 10, so A. If we convert that into decimal now, so 15 multiplied by 1 plus 7 multiplied by 16 plus 10 multiplied by 256, we will get 2687. This numbering system is often used by computer system designers and programmers as they provide a more human-friendly representation of binary coded values. In our case, we have to understand the hexadecimal numbering system as it is used in network addressing. So for example, MAC addresses are written in hexadecimal as well as IP version 6 addresses.